Yeah, welcome everyone to this third session on random matrix theory. So this one is going to be a little bit special because, well, one is that I didn't have all that much time to get a lot of slides, so the theory will be fairly light today. It will be mostly enough theory to understand the two papers that we've read. So there's like a couple of papers applying RMT to machine learning. We covered two today, and we'll see. Yeah, I have mixed opinions about them, but we'll see. Oh, the arrow keys do not work. Oh no. Okay. Yeah, so the outline is basically first, chapter 5, the joint distribution of eigenvalue and eigenvalue spacing. Uh, Really, this will be very short because the chapter 5 has a lot about edge statistics and like different ways of computing the eigenvalue distribute density, which we won't go into. We'll be mostly talking about another property of random matrix theory, which is the distribution of the distances between neighboring eigenvalues. And this will be relevant to the two applications that we'll be talking about next. So we'll be talking about two papers, one being appearance of RMT in deep learning. I think I have the archive linking later down the slides. And then the second one is traditional and heavy-tailed self-regularization in neural nets. So these are two papers using RMT to like examine something in neural networks, but let's not get ahead. Right, so as a quick little recap, so right, last time we talked about Wishart matrices, which are sort of the default or standard model in random matrix theory for talking about covariance matrices of presumably Gaussian variables. So the idea is that we have W being so 1 over T, the 1 over T is just a normalizing factor times H times H transpose. So this would be the covariance matrix if H was some variables. And H we can assume for now to be essentially a sample from a normal distribution with unit variance, but we saw last time how to handle different variances. And the important parameter here was the rank, quote unquote, parameter Q being the ratio of n, so the number of variables times the number of samples you have of those variables. And specifically, we'll be looking at the case where we have more samples than variables here. In practice, it doesn't change much. It just changes a little bit, a few things about this distribution, but otherwise it's the same. And yeah, last time we saw that the eigenvalue density of these matrices, so like if you're looking at the eigenvalue density of this W matrix, that means we're looking at the density of the singular values of these matrices H. And so what's nice that if we have like a rectangular matrix, okay, it's not squared, but we can at least talk about the distribution of its singular values. And so, for example, for our neural network with like rectangular matrices for the weight, right, we can apply these, try and fit these models. So yeah, for Wishart matrices, the distribution will look a bit like something like this. So notice that it has a strict bound. So the support of this distribution is finite and doesn't go like crazy. There's no crazy tails here, which will be an important feature related online. So let's start with just the theory for this part. So chapter 5 was about the joint eigenvalue distribution. So to recall, like this distribution here, it's the density for a single eigenvalue. And okay, if you take many samples of your matrices and compute their eigenvalues and put a histogram, it will fit this distribution reasonably well. But when you sample the eigenvalues, right, they're correlated because when you compute the eigenvalues, it's a function of all the entries of your matrix, and so a given set of eigenvalues is not they're not sampled independently. And so it's actually fairly easy to compute the joint eigenvalue distribution, at least in the case where you have so rotationally invariant random matrices. So remember, those are the matrices that had boring eigenvectors in the sense that really the set of eigenvectors is uniformly distributed. And and so there's not much point in looking there. So the only thing is interesting is the eigenvalue distribution. And for so these matrices that have boring eigenvectors, they could be expressed in a general form as this. So we have first a normalizing factor, so z, and the exponential of minus n over 2 times the trace of some function v of our matrix M. And v is called something called the potential function. It could be, for example, a polynomial or something else. So, for example, for the Wigner ensemble, right, the first basic random matrix distribution that we saw, this would simply be the x squared over 2. For the Wishart ensemble, this is a bit more complicated. We have x plus something times log x. Here it's log for the natural log, I think. So in the book there's a general recipe for computing the joint eigenvalue distribution of this family of matrices, and they're actually fairly general. So given the the way we do this is that we first take the eigen decomposition, M equal, so O being orthogonal, the matrices of eigenvalues lambda and then O prime, and we compute the joint eigenvalue distribution of the eigenvalues. And how we do this, I'm waving my hands quite a lot here because it's a bit involved, but at the end it's just about a lot of calculation. But roughly, right, we have a probability for the entries of the matrix M. And so the idea is that first because we know this probability, we can sort of re-express it as a function of O and lambda. And here, in this case, we'll be going from M to lambda and O. And when computing the probability for this will basically just introduce a factor, so the absolute value of the determinant lambda, where lambda is this matrix here, basically the Jacobian of M relative to lambda and M relative to O. Long story short, the Jacobian of M relative to O is fairly boring. It's not it basically does not really affect the eigenvalue distribution as we should expect, right? If you just change the eigenvectors, that shouldn't matter. And the Jacobian with respect to the eigenvalues is a bit more simple. And the long story short is that we can express this absolute value of the determinant as the product of all, essentially all pairs of different eigenvalues, take their difference in absolute value and take the product of that. And because we have, so this only depends on the eigenvalues, and because our probability here is just a function, the exponential of the trace, and remember the trace is just the sum of v applied to each eigenvalue at the end. That tells us that the joint distribution of eigenvalues, so the probability of getting a given set of eigenvalues lambda I, is going to be proportional, so up to some normalizing factor, to this product of so pairs of eigenvalues in absolute value and take the distance between them, times the exponential of this sum of v applied to lambda I. And so, okay, the interesting part here is that because we have these products, and especially because this, let's say, look, if lambda L is equal to lambda K, this is 0, so we get that the probability of two eigenvalues being equal is 0. And so that means that in general, the eigenvalues won't be independent, they'll be correlated, and in particular, they have a bias towards not being equal, as is shown here. And if you look at if you were a physicist, this would look, you could interpret this as essentially saying that the eigenvalues work a bit like particles of gas. So you could imagine each particle being like a point moving in either on constrained to the real line or just the complex space. And imagine it's a particle that's trying to minimize some potential, here just V, but they have some repulsive interactions. So they like they're particles and they don't want to get too close. And we can sort of see this if we take the the log likelihood of our model. So we have like the probability being essentially proportional to the exponential of something that depends on this likelihood function of the eigenvalues. And this likelihood function, or log likelihood, is simply the sum of our v, so the potential applied to each eigenvalue, plus this repulsive terms, repulsive force that depends on each pair of eigenvalues. So so far so good. So what makes this nice is that it gives sort of a, at least for physicists, it gives a nice interpretation, and for us, it tells us, oh, well, this looks a bit like you're trying to regularize something. So you could also interpret this log term here as a kind of regularization towards having eigenvalues being equal. This has one sort of nice thing is that if you have like two eigenvalues equal, that tells you that there's you don't know exactly what the eigenvectors look like, right? Because if you have twice an eigenvalue, that means you have at least let's say a subspace of dimension 2 with that eigenvalue, and that means that basically any basis of that subspace would work, and so that means you aren't sure about exactly what your eigenvectors are. Whereas if you have this, you know that no two eigenvalues are going to be the same except in very special circumstances. And so you know that there's no like ambiguity as to what eigenvectors you're going to get. Okay, so that was the theory for this part, and let's finish with sort of like a nice example of this. So this distance between eigenvalues, so it's a famous result called the Wigner surmise, which Wigner derived for Wigner matrices. And basically, he look at like if you look at like a Wigner matrix with just two size two, so n, so two by two, it has only two eigenvalues, and you can sort of easily show that the probability of the distance between the two eigenvalues follows this. So it's basically a linear map, or just a linear term times a Gaussian. And so it looks a little bit like this, up to some normalization so that the distance is one, or the average distance is one. And we do see, in fact, that okay, there's very low probability of having eigenvalues like exactly equal or near each other, and there'll be more like bias to be at least at some distance. Okay, so that was for the theory. Any questions so far, or can we move on? Okay, so still no one talking, so let's continue. So the first application is this paper. So I have the link here. Also, appearances of random matrix theory and deep learning. Um, to be fairly honest, I'm a bit disappointed by this paper, and we'll see exactly why. So what these guys did was they looked at the spectral statistics of the loss Hessian. So you look at like the Hessian matrix of your loss at different points. That's a matrix. One unfortunate thing is that the larger your model, the more difficult this becomes to compute. And so they could only look at small models, which was a bit of a problem. And okay, they mentioned existing results that the, the the spectral density of the Hessian does not match the classical ensemble. So it's not a Wishart, it's not a Wigner matrix, it's not anything really well understood. But they do mention that okay, while the exact density does not like match anything we know, the distances between two like nearest eigenvalues they do match what we know, so they do follow this sort of Wigner surmise. But then again, I sort of didn't really get their conclusion because a lot of matrix ensembles sort of verify this, so it's not clear exactly what to conclude from this paper. So yeah, I was a little bit disappointed by this paper because okay, they look at the spectral distribution, they say, oh yes, yeah, so it does look like a Wigner surmise. Okay, cool, and unfortunately, their paper doesn't really say much about that. They just say, oh, if this wasn't the case for larger networks, it would be interesting, but they don't look at larger networks. So I'm not really sure what to conclude from this paper other than okay, uh, there is one thing that works like random matrix, but it doesn't really tell us anything about how neural networks function or really anything else. So yeah, that one was short, but the second application I thought was much more interesting. So it was traditional heavy-tailed self-regularization in neural network models. So there it was this paper, which is basically the short version of the second one, which basically just gives a lot more details, but even the short one was very interesting. So what these guys did, they looked at not the Hessian, but the singular values of neural network weight matrices. And so, as mentioned in the beginning, like this would be like a good thing to apply Wishart matrices and Marchek and Pasteur distributions to. And what they find that first of all, they identify sort of 5 different phases of eigenvalue densities. And most importantly, so the older models, so they looked at like stuff like LeNet and AlexNet, so these older models, and especially LeNet, they would find that these models have eigenvalue densities that look like Marcheco-Pasteur, so they they were approximated by this. But even AlexNet, for example, they do not follow this Marcheco-Pasteur distribution. Instead, they follow a power law. And whenever a physicist sees a power law, he usually gets very excited, although for much different reasons that like machine learning people get excited about power laws, but we'll get to that. So yeah, basically what they observe that there's a bit of a transition between older models and simpler models that have this more Pacheco-Pasteur distribution and new models getting a more and more power law distribution. So just a brief recap about these power laws. So here, for example, if you assume that you have a weight matrix whose entries are sampled from a power law that looks like this, so you have the mu parameter that's positive, and so if you were to look at this in a log-log plot, right, this would be a straight line going down. Usually you'd have to like truncate it at some point, but that's the main idea. And they sort of mention, okay, some different like regimes. So if you have like mu larger than 4, then it's not really interesting because asymptotically the eigenvalue distribution or density will be a Marcheco-Pasteur distribution. Where it gets a bit more interesting is in the when you're uh, less than 4, so especially between 2 and 4. Well, at finite size, you get something that's also a power law, but you have to fit the parameters. So you have lambda to the minus a mu plus b, and you have to fit them, and there's some like finite size variations, finite size effects. And as n goes to infinity, it converges to this lambda to the minus 1 minus mu over 2. And then if you go even stronger, so mu between 0 and 2, then it converges much faster to this like asymptotic distribution, and the smaller, this like the small size, finite size effects are also much smaller, so there's less variations. And as a side note, so I mentioned that physicists get really excited about power laws. The reason is that, especially in statistical mechanics, power laws, they usually tell you that there's something weird going on. Like you have stuff like either fractal structure or long range correlations. You have like, yeah, really complicated structure that appears in your system that is not random. So generally, this would be like stuff like the brain or stuff like the internet. Anytime you see a power law, it usually tells you that there's a really complicated phenomenon going on. And so to see this appear in in machine learning, that might be an explanation, for example, why maybe a model learns features. So let's move on to the phase of regularization. So the short idea, right, is that you assume that you take one like weight matrix in your models and assume it has the form of some noise plus some signal. And depending on like the ratio of noise to signal, will get different things. Especially signal, we will assume that it'll be following this kind of power law distribution. And so if like the noise is much larger, for example, as we saw in the Lunette, then we see that it's basically a Marcheco-Pasteur distribution. It's well approximated by it. Then so that's the what they call the random like because it's basically a just like a Marcheco-Pasteur, and they also mentioned that you could also interpret this as basically Tikhonov regularization. Tikhonov regularization just means either ridge regression or L2 regression, so just bog standard Gaussian prior on your weight. If we go to the next phase, it's a bit different, right? It's still mostly well fitted by a Marcheco-Pasteur distribution, but there's a bit of mass, like probability mass, that goes like that escapes. And so they call that the bleeding out phase because you have a little bit of probability mass that is not following a Marcheco-Pasteur. And basically the rest is the continuation of that. So next one, bulk plus spikes. Well, you see that you have the bulk that follows a Marcheco-Pasteur, but that you have a bunch of eigenvalues that are like that had completely escaped, that are separated from the bulk. And this goes on, and then you go to the bulk decay, where okay, you still have these spikes, and the bulk starts to be less and less well approximated by Marcheco-Pasteur until you reach the full heavy tail stage, where it's just a power law, and at this point you get interesting things happening. They do also have like a final like phase, but it's more like predicted by the theory, but it's a degenerate case because they call that the rank collapse because most eigenvalues are zero, and so that would indicate that you've like regularized way too much, and so you have just completely destroyed your model. So one of the more interesting things that they observed, so they did observe all these phases in like various models. For example, in Lunette they had this either the like random like or bleeding out maybe phase, but then for AlexNet it was clearly more of a power law. And another thing they explained is that they took a model, so I think yeah AlexNet, and they just tweaked the batch size to display these different like phases. And they link that to something called the generalization gap, which is this idea that actually if you take larger and larger batches, your model like overfits and performs worse, which is a bit counterintuitive, right? You'd expect that using a larger batch gives you a better estimation of the gradient, and so your model should perform better, but actually no. So they do show that if you take AlexNet and use a batch size for 500, for example, it's in this random like, and then as you decrease the batch size, you go through all 5 phases. So from first the bleeding out, then the spikes, and then yeah, bulk decay until you get the power law with size 4 or 2. So this one I thought was particularly interesting because it indicates a lot of like interesting things happening. Okay, I see someone writing a question. How do we reconcile these with certain models preferring huge batch sizes? Um, Good question. I don't know. So yeah, transformer models, contrastive width models. Hmm. I'm honestly not probably qualified to answer that, but I guess the architecture does a lot here. But at least, yeah, I think. Hmm. Yeah, if someone has a better answer, please do. But I think the small batch makes sense if you think of it as approximating Bayesian inference. Very small batches, you're doing something closer to sampling for the posterior than to choosing the maximum likelihood estimator. Yeah, Yeah, I think that's interesting. In the paper, as justification, they were mentioning if you take a too large a batch, you sort of like destroy um, some small correlations between your data points that you can only really get looking at small batches. I don't really know how much that makes sense. Yeah, the too large, but yeah, definitely the too large batch effect is seen in practice. I've been talking with like ML people at my uni, and I mentioned, oh yeah, if you take a full batch, actually your model will overfit, which was surprising to me. Keeping in mind that okay, even though they've like used different batches, like it's not clear that this is a better performing network than this one or this one. Sigmoid loss. Yeah, maybe contrastive is a little bit weird and strange. Probably transformers are a bit strange too, right? Because they also I think they're not the training process is also not like the standard one you'd have. Oh, okay. Yeah, so that's the end of my slides, but I have the papers. Let's see. Yeah, there we go. Because the papers have mentioned a few other things. So yeah, for example, this one, I think they mentioned also something about eigenvector localization. So what happens there is that your eigenvector basically becomes sparse. Like there's only a few entries that are non-zero, and the rest is basically zero. So one way to interpret is, oh, your eigenvector is becoming sparse. Maybe that means you have like feature learning going on or something else. But it also means that if your eigenvectors like become this way, it also means that you're no longer in the like um, rotationally invariant regime because you have like these very sparse eigenvectors, which you wouldn't normally get. So they mention a bunch of things. I think they had yeah something looking like this. So the stable rank. So they have this metric called the stable rank. I think they defined it somewhere, but maybe not clearly. Probably in the main paper. Anyway, okay, so the short one doesn't have that much. Maybe, no, that's not the paper. Okay, so this is the big one. I think the big one has a lot more about their examples and their methods, so probably worth looking at. So, yeah, a short one this time, but anyone else have questions? Nope, but I'll comment that I think the slides were pretty. Yeah, thanks. I made them using Typist. Just, yeah, trying it out. It's nice. Also the other really nice thing, let's see. Right, this plot, you may see that the font here is the same as this font. I didn't do that on purpose. It's just type because this is an SVG plot, and when Typist sees an SVG, it like uses the proper font. So that's pretty cool. I think even for the road it has a special character. That's interesting. So yeah, I'm pretty pleased with the slides too. Anything else other than the slides? So that's why it kept fucking with my SVG text. Maybe. Oh yeah, I did have like an interesting thought about their parallel results. Is that so? Like the whole thing they were saying is that these different phases of uh, like these different phases could like sort of correspond to different like different like types of regularization. So the first one would be like essentially L2 regularization. And they mentioned, okay, if you have like this parallel, that would mean you have like a different type of regularization towards having your your eigenvalues being parallel, but you could also say your weights are parallel. So I wonder like if people have looked at essentially if you look at this in a Bayesian way, you like have a parallel prior on weights, and maybe that changes something. I think I do believe a few people have looked at that already. Yeah, maybe like parallel in it, um, or maybe just like a regularization. So maybe you don't initialize your weights as parallel, but you have like a yeah, that's a parallel in it. Yeah, of course. Um, like maybe you don't initialize your weight as a parallel, but maybe you have essentially a regularizing term that's essentially the log likelihood of a parallel on your weight. Yeah, yeah, I will comment on the SVG thing. So sometimes text on HVG just disappear. I've noticed sometimes when I have like a SVG in Inkscape with text and write it, the text disappears. So I don't think typist is the only one to blame here. Is there a particular power it tends to? One of our skill very Jeffrey priors. Huh. I think, yeah, I do think the dimension, so the power would be one over the square root. Wait, actually, no. So mu. Uh, is there actually power? Let's see. So something about the eigenvalue distance and how it could be interpreted. Okay, I'll get to that. I'll try and see if there's like any indication of like the power law distribution that this converges to. I think they do mention that the fitting power laws is a bit difficult because there's a lot of noise. I think they have some plots in the appendix that, okay, not here, but somewhere along there they had some, or maybe in the other paper they had some plots that weren't looking all that great. Um, yeah, think I don't think they actually give an explicit. Oh, good fit for alpha being 2.25, so mu smaller than 3. So that would be Yeah, so that would be a bit more than 1 over x squared, actually. So not the Jeffrey priors. Okay, so the stuff about the eigenvalue distance and how it could be interpreted. So do you mean stuff I said about this this part or this part? The latter. Okay. Um, no, the latter slide. Okay. So right, so this thing, right, you're looking at the log likelihood of the eigenvalue density, or not the eigenvalue density, the joint eigenvalue probability. You look at the log likelihood of it, and it's a term that depends on the potential applied to each eigenvalue. And you have this term, the sum of log absolute value lambda I minus lambda j. What this looks like is that you're trying to minimize this, but you have this constraint that your eigenvalues cannot get too close to one another, right? If two eigenvalues would get too close, then like the log will explode, or no, actually the log will be go to minus infinity, but because you're trying to maximize log likelihood, um, you want to avoid that. So you want the eigenvalues to be sparse, not sparse. You want the eigenvalues to be different from one another. Maybe you're thinking about the stuff I was saying about the eigenvectors. Okay, so that was the your question, not the eigenvectors. Okay, if you're still confused, then do like chat out in the thread. So yeah, I think we've covered most of it. Although yeah, I think I will read the second paper a bit, like the long version probably a bit more, but otherwise, yeah, I think we can wrap it up. I have no idea when the next one is going to be or what about, so I'll post a mini poll as always. So yeah, stay tuned for that.